Good morning. My name is Derek Edwards, and I wanted to share with you some things I've learned about quantum computing. The things I've learned about quantum computing come from a graduate certificate in quantum computing that I've been taking. About me, I'm a computer guy who has studied quantum computing for the past couple semesters as part of a graduate certificate program at the University of Rhode Island. What that means is that I'm not deep in physics or even quantum physics, but I do have over 30 years experience in systems and software engineering and cyber security. So, per IBM per IBM, quantum computing is an emergent field of cutting edge computer science, harnessing the unique qualities of quantum mechanics to solve problems beyond the ability of even the most powerful classical computers. So the purpose of quantum computing is to solve problems beyond the ability of even the most powerful classical computers. And we've been using a textbook in our classes called Mermin textbook, or written by Mermin, and it says that our laptops operate under the laws of quantum mechanics, but they're not a quantum computer. And the distinction is that a quantum computer is one whose operation exploits certain very special transformations of its internal state. And the laws of quantum mechanics allow these peculiar transformations to take place under very, very carefully controlled conditions. So the laws of quantum mechanics govern the interaction between electrons and the computer chip, and the Wi-Fi antenna, but it's not the same as being able to manipulate the quantum properties of the atoms in the computer. Internal state is captured in qubits, and so a qubit is a quantum bit, which is kind of like a classical bit, which is a binary digit. And yes, the states of a qubit, yes, they include the one state and the zero state. Zero state is represented by this vector here. Likewise, the one state is represented by this vector. But the states are vectors that are defined by two complex numbers. Complex numbers mean that each number could include a factor of the square root of -1. State vectors are normalized to map onto a sphere with radius 1. Okay, and so they are visualized using a block sphere. So when we talk about transformations of internal state, these transformations are linear. They're rotations like multiplication by the Pauli X gate. So here we have a representation of a quantum circuit wherein we've set the initial state as the zero state, and we apply the X gate. And what that gives you is this mathematical matrix multiplication, which leads to the one state. You can see ket one here. And so that's right, that gives you one. And the block sphere visualization is a 3D mapping of a more than 3D space. And you can see before the arrow was pointing up toward the zero state. And so after application of the X gate, now the block sphere shows an arrow pointing generally down. So it's a block sphere's visualization of 3D mapping of a more than 3D space. So though the zero state and the one state are orthogonal, perpendicular, the block sphere shows them as antipodal. A qubit can be in a superposition, and that means that a qubit can be in two or more states at the same time. But when measured, the outcome is one of the possible states. And so it's kind of like a coin spinning on its edge. So as long as the coin is spinning, you could get a zero, you could get a one. But once the coin stops spinning, it's going to settle on either on the heads side of the coin or on the tail side of the coin. And when demonstrated over many trials, what we'll find is that we'll get the heads result with a half probability approximately, and the tails side will be up with a half probability. Okay, and likewise, in our quantum circuit, we can apply the Hadamard gate to the 0 qubit, and what we'll get is we'll get this superposition, right? Where you have a superposition of the 0 state plus the 1 state. And if we apply the Hadamard to the 1 state, you get the 0 state minus the 1 state. And you can see that there's a difference in sign, which means a phase shift, phase difference. Entanglement. Qubits can be entangled. So where changes to 1 qubit in an entangled pair will also take place on the other qubit. And that is durable within the quantum machine until measurement. And so the Bell circuit is one such example of entanglement. And so here's a Bell circuit. We have 2 qubits, Hadamard gate. This is called a controlled NOT gate. And here we're measuring the output of those 2 qubits. And so when we take this experiment over a number of trials, here 512 trials, what we'll find is we'll get a superposition of the 0 state and the 1 state, representing 0 and 3. But what happened to 1 and 2? And so 4 possible states of, the way you can have 4 possible outcomes of 2 bits. You can have, with this entanglement, you only get 2 of the possible states. And so it's not known exactly how or why entanglements works. Interference, where it's desirable and expected, where we have interacting waves in phase which reinforce one another. And then we can also have interacting waves in an opposite phase which cancel one another. And so our strategy is to reinforce the answer we're looking, or reinforce the answer to the quantum circuit. And then we want to get other values to cancel out. And there's unwanted interference, which we call decoherence. And it drives costs. It's caused by internal crosstalk and interaction with the outside world. And its effects are errors in results and inability to scale circuits, because error correction often requires additional qubits to be added to our circuits. Hence the phrase, under very carefully controlled conditions. So error correction, due to decoherence, you could have a bit flip. That's one where what we expect is for there to be a 0 state and we get a 1 state, or there could be a phase flip where the superposition we intend is to have a -1 state and we get the +1 state instead. And then there's also gate noise, where the gates may not, the gates have some error in the rotations that they impart. So what to do? We add qubits to detect and correct single qubit errors. And so it's, you add redundancy to the circuit. It's kind of an engineering or cross-engineering disciplines. That's one way. And it multiplies the circuit's size, tends to add noise. And this is still a hard problem that the science and the engineering are still working on. The circuit model that we have is the Deutsch-Jozsa quantum oracle model. Historically, an oracle is a person about whom not much is known, gives advice, gives divine answers to our questions. And the process for attaining those answers is hidden. Mathematically, in a Deutsch-Jozsa circuit, we have to have the same number of inputs as outputs, and those functions are reversible. Um, Practically, the Deutsch-Joseph quantum oracle model represents an abstraction and allows us to discuss the questions and the answers and get agreement on how to build in advance of knowing, deep details about the how everything works together. Um, so transpilation is an internal process that brings quantum computers to realization. First, the circuit is packaged into a DAG, which is a directed acyclic graph. Arrows show the dependency relationships, and acyclic means directions do not go in a circle. Once optimized and mapped, then the DAG is transmitted to a back end for execution. So there's optimization to find the most efficient circuit for the machine. And then there's mapping to the machine's physical qubits based on connectivity, noise, error performance, and other factors. And we will also want to map to the machine's native gate set. So here we see the Bell circuit we had with 2 qubits, and they're mapped onto qubit 97 and qubit 96. There's a number of gates that are used to implement the Hadamard and the controlled knot. So RZ gates, SX gates, RZ, SX, RZ, and then ECR gate, RZ, and SX. So that's part of the native gate set. And so you could see when 127 qubit machine, which is this graph, normally it's a very wide graph because it shows all 127 qubits. And but it only shows that our circuit is mapped to qubits 96 and 97. Circuit is sent to a back end. So the back end, the chip, the actual quantum computer is on this chip, but there is all this plumbing, which is part of, and put in a refrigerator. Remember we talked about strictly controlled conditions. It's in a refrigerator to cool that chip down to a very low temperature to control noise and those sorts of things and those sorts of things. There are waveform generators and digitizer machines that are in those wires to stimulate the qubits and control the qubits, and then there are digitizer machines to get the results. And so all those interactions are scheduled centrally. The output can be visualized in a state vector, which shows the result of one shot in a block sphere. Then there's also running the circuit thousands of times, hundreds of times, and you can show the counts of the outputs of the outcomes on a histogram. Then there's also the estimator. So you can find the average values of circuit outputs with respect to a given direction, or what IBM calls an observable in a certain basis. Okay. And so the purpose of quantum computing is to solve problems beyond the ability of the most powerful classical computers using the quantum, the principles of quantum mechanics, which include superposition, entanglement, interference, and error correction. And the way that is done using circuit transpilation. So we create a circuit. That circuit is packaged as a DAG, just a directed acyclic graph to be optimized and transmitted to the back end. And that optimized DAG is mapped onto the target quantum machine, and then that circuit is run, and the results are presented and visualized. I hope that helped you to understand a little bit about how quantum computing works, and wish you success on your quantum learning journey. Go ahead and send me a comment if you have any questions about this video. and look forward to hearing your comments. And thank you so much for watching. Bye bye.